That stone in your hand could be older than every dinosaur that ever lived. This is the geological clock, the story of our planet written in rock. By the end of this journey, you will be able to look at any landscape and read its hidden history. We will uncover how a single global layer of clay marks the day the dinosaurs died, and how tiny crystals hold the secret to Earth's violent birth. What does the ground beneath your feet remember? This geological clock is not a machine with gears and hands. It is a story. It is the epic tale of our planet, written in layers of mud, sand, and ash. The concept was born from the curiosity of early thinkers who walked through canyons and saw not just walls of stone, but a library. They realized the Earth itself was keeping a diary. One of the most important of these thinkers was a man named James Hutton. Looking at the slow, patient work of rivers carving valleys and volcanoes building new land, he proposed a powerful idea. The present is the key to the past. The forces that shape our world today, the gentle rain and the shifting stream, are the very same forces that have been sculpting the continents for eons. This principle unlocks the entire narrative. It allows us to interpret the past by observing the present. To read this story, we first need to understand its grammar, the basic rules of how the pages are stacked. The first rule is called superposition. It is beautifully simple. In any undisturbed pile of sedimentary rock, the oldest layer is at the bottom and the youngest is on top. Think of a stack of old newspapers in your basement. The paper from last week sits on top of the one from last month, which sits on top of the one from last year. The rock record works the same way. The second rule is original horizontality. This means that all these layers of sediment, whether sand on a beach or silt in a lake, were originally laid down in flat, horizontal sheets. When we see them tilted or folded today, we know a tremendous force, like the collision of continents, has moved them since their birth. These two simple principles, superposition and horizontality, are the ABCs of geology. They give us the initial framework to look at a cliff face and understand the sequence of events, to know which chapter came first. But how do we move from the relative sequence of events to knowing their absolute age in years? How do we attach real dates to this profound story? These layers of stone are the pages of our planet's diary, and each page is written with a different kind of ink. The materials that compose these historical records tell us not just when something happened, but what the world was like at that exact moment. Think of a layer of coarse, gritty sandstone. This is the signature of an ancient beach or a riverbed, a place where strong currents could carry and deposit heavy grains of sand. Now picture a layer of fine, smooth shale above it. This mudstone forms in the quiet, still waters of a deep lake or a calm sea, where only the tiniest particles can slowly settle to the bottom. This sequence tells a clear story. First, there was a vibrant shoreline, and then the land sank or the sea levels rose, submerging that beach under deeper, calmer waters. A seam of coal reveals a swampy forest, teeming with life, that was later buried and compressed. A band of limestone speaks of a clear, warm ocean, alive with shelled creatures whose remains built up over millennia. Every rock type is a clue to a lost environment, a fossilized ecosystem waiting to be read. Yet these layers of mud and sand are only one part of the story. To truly synchronize Earth's diary, we need a universal timestamp, a biological signature that marks the same moment in time from one continent to another. This is the power of the index fossil. Think of a creature like the trilobite. These ancient marine animals evolved rapidly and spread across the globe, but each distinct species existed for only a short, well-defined sliver of geological time. When we find the exact same trilobite species fossilized in a cliff face in England and deep within a rock quarry in India, we have discovered a profound connection. It proves that those two layers of stone, despite being made of different materials and separated by thousands of miles, were formed simultaneously in Earth's deep past. This practice of using fossils to date and correlate rock layers is called biostratigraphy. It turns isolated rock formations into a single, synchronized timeline. These biological markers are the golden spikes hammered into the geological record, creating a global calendar of life. A specific ammonite shell becomes a precise timestamp for the Jurassic, just as a particular type of graptolite fossil defines a moment in the Ordovician period. With these keys, scientists can take the scattered pages of Earth's history and assemble them into a coherent, planet-spanning narrative. But what if we need a date more precise than a fossil can provide? What if we want to know the exact year, or even the season, of a cataclysm that occurred millions of years ago? For that, we must turn from the biological clocks to the chemical ones, to the very atoms that make up the rock itself. To build a clock, you need a mechanism that ticks with perfect regularity. Deep within certain crystals, we find such a mechanism, an atomic hourglass that started the moment the mineral formed. This is the principle of radiometric dating. Certain elements, like uranium, are unstable. Over vast stretches of time, their atoms spontaneously transform or decay into different, stable elements like lead. This decay happens at a rate so consistent it is known as a half-life. A half-life is the time it takes for half of the parent atoms in a sample to decay into the daughter product. If you begin with 100 atoms of a radioactive element after one half-life, you will have 50 atoms left. After another half-life, only 25 remain, and so on. By carefully measuring the ratio of parent to daughter atoms in a crystal today, scientists can calculate backwards to determine the precise moment that crystal locked those radioactive elements inside its structure, the moment it started keeping time. The development of uranium-lead dating was a true revolution. By applying this method to the oldest minerals we can find, tiny zircon crystals from Western Australia, geologists determined our planet is about 4.54 billion years old. This single number gave the entire geological timeline its foundation. It transformed our relative sequence of rock layers into an absolute calendar, placing precise numbers on the face of the great geological clock. But for this atomic clock to work, the mineral being dated must be a perfect time capsule. It must have been sealed at the moment of its formation, preventing any atoms from escaping or entering over the eons. This requirement leads us directly to the most resilient timekeepers on Earth, the zircon crystals. These tiny zircon crystals are geological survivors of the highest order. Formed in cooling magma, they possess an almost indestructible structure that locks uranium atoms inside their lattice the moment they crystallize. Think of them as nature's ultimate time capsules, sealed against the ravages of time. Unlike other minerals that break down or reset their clocks when heated, zircons are incredibly stubborn. They can be eroded from their original rock, transported by rivers, and cemented into an entirely new sedimentary layer, all while preserving their original radioactive stopwatch, still ticking from their moment of birth. This resilience means that within a single piece of sandstone, you might find a collection of zircon crystals, each one telling the story of a different, much older volcanic event that contributed sand to that ancient beach. It is like finding pages from several different diaries bound together into one volume. The most ancient of these zircons, discovered in the Jack Hills of Western Australia, are themselves over 4.4 billion years old. But their story is even more astonishing. By analyzing the specific types of oxygen atoms trapped within these ancient crystals, scientists found a signature that could only have come from rocks that interacted with liquid water. This single piece of evidence rewrote our understanding of the Hadean Eon. It tells us that even in that first 500 million years, when Earth's surface was thought to be a global ocean of magma, there were already patches of solid crust and, most importantly, pools of liquid water. The planet was not a perpetual hellscape, but a world already cooling, already becoming hospitable, almost from the very beginning. This profound transformation from a molten ball to a world with oceans set the stage for the next great act in Earth's history, a change so dramatic it would fill the skies with a new color and poison the very air for the life that was already there. The world's first pollution crisis began with a color change. For over 1 billion years, the ancient oceans were a soupy green, rich with dissolved iron. Then, a new form of life learned to harvest energy from sunlight. Tiny cyanobacteria began exhaling a toxic waste gas, oxygen, into a world that was utterly unprepared for it. This was not a gentle transition, it was a planetary upheaval written in stone. You can see its record in the stunning banded iron formations, rocks with beautiful, rhythmic stripes of rusty red and deep gray. Each band is a page from that ancient crisis. The red layers are iron that rusted out of the seawater when oxygen levels temporarily spiked, sinking to the bottom in a perpetual chemical snowfall. The gray, silica-rich layers represent quieter times when the iron slowly built up again. This slow, rhythmic pulsing created a geological tape recording of the Great Oxidation event, a 200 million year period where biology first seized control of the planet's chemistry. This rusting of the oceans was a necessary catastrophe. It cleared the waters of soluble iron, paving the way for free oxygen to finally accumulate in the atmosphere, forever changing the sky from a hazy orange to the clear blue we know today. This new, oxygen-rich world was a death sentence for the ancient, anaerobic life that thrived before, but it was the single greatest opportunity for everything that followed. Our very existence is a consequence of that ancient rust, yet this new atmosphere, born from crisis, would soon plunge the entire planet into the most extreme climate event it has ever experienced. A lone boulder of granite rests in a field of limestone, a geological stranger in a foreign land. These are glacial erratics, immense stones that were plucked from their birthplace and carried hundreds of miles by continents of ice. They are the forgotten luggage of the ice ages, dropped haphazardly when the glaciers finally retreated. To understand their journey, you have to read the ground they traveled over. Run your hand over a smooth expanse of bedrock, and you might feel long, parallel grooves scratched into the stone. These striations are the claw marks of the glacier, a direct record of its immense weight and gritty passage. By mapping the trails of erratics and the direction of these scratches, scientists can reconstruct the flow of ancient ice sheets with astonishing precision. They reveal that only 11,700 years ago, much of North America and Europe lay buried under ice more than a mile thick. This recent ice age is a fresh chapter in the rock record, a clear warning of how the planet's climate can pivot between two radically different states. We have greenhouse worlds, warm and lush, and icehouse worlds, locked in a deep freeze. These cycles are the planet's long, slow pulse. But the geological clock also records moments of sudden, violent change, events that are over in a geological instant but leave a scar that lasts for eons. There is a single terrible day written in stone. You can find its mark almost anywhere on Earth, a thin, dark line of clay no thicker than your finger. This is the KPG boundary, the geological signature of the asteroid impact that ended the age of the dinosaurs. This line is a perfect timestamp, a global bookmark placed 66 million years ago. The key to its story lies in a single, surprising element: iridium. Iridium is incredibly rare in the Earth's crust, but it is common in metallic asteroids and other space rocks. When scientists first discovered this iridium-rich layer in Italy, then in Denmark, and then all over the world, the conclusion was inescapable. A massive object from space had struck the planet, vaporizing on impact and spreading a cloud of dust, soot, and extraterrestrial iridium across the entire globe. This dust cloud blocked out the sun for years, collapsing food chains and leading to the extinction of nearly 3/4 of all life. The rock record shows this change with brutal clarity. In places like the Hell Creek Formation in North America, you can place your finger on this line. Below it, in older rock, you find the massive bones of Tyrannosaurus and Triceratops. Just above that line, in younger rock, the giants are gone. The fossils are smaller, the bones of mammals and birds, the survivors who inherited a shattered world. This is the geological clock recording a true catastrophe, an event that was over in a day but whose echo shaped the next 66 million years. Yet for every sudden strike recorded in stone, there is a force of almost unimaginable patience, a process so slow it makes mountains seem fleeting. The slowest and most powerful force on the geological clock is the movement of the ground beneath our feet. Continents are not anchored in place, but drift like colossal rafts on a layer of hot, pliable rock, their journeys measured in centimeters per year. This is the grand, unifying theory of plate tectonics, the engine that drives the planet's long-term pulse. The most dramatic evidence for this motion is written in the sky itself, in the form of the Himalayan mountains. These towering peaks are the direct, ongoing result of the Indian subcontinent smashing into the underbelly of Asia, a collision that began roughly 50 million years ago and continues to this day, pushing the mountains a little higher with each passing year. This is geology in real time, a slow-motion car crash preserved in rock. But how could anyone have ever guessed that continents move? The proof was not just in the mountains being built, but in the patterns of life shattered by their creation. The discovery of identical fossil species on continents now separated by vast oceans was a geological mystery that only drifting continents could solve. The fern known as Glossopteris, for example, left its distinctive fossil imprint in the rocks of South America, Africa, India, and Australia. This plant could not have sprouted from seeds carried across thousands of miles of salt water. The only logical conclusion was that these lands were once a single, connected forest, later torn apart by the relentless drift of tectonic plates. This biological clue was a key that unlocked the past, proving the existence of the ancient supercontinent Pangea. The rock record preserves the entire cycle of this grand dance, from the rifting apart of continents to the birth of new ocean floors at mid-ocean ridges, and the eventual, inevitable collisions that build new mountain ranges. It is a story of continuous creation and destruction written on a planetary scale. To understand the finer details of this story, we must look beyond the shape of the continents and into the very chemistry of the stones themselves. The stones beneath our feet remember the temperature of the air and the chemistry of the oceans. While the shape of a rock tells us about physical forces, its atomic structure holds a detailed diary of the ancient climate. To read this diary, scientists use tools called geochemical proxies, chemical fingerprints locked within minerals and fossils that reveal the precise conditions of their formation. One of the most powerful of these proxies comes from the microscopic shells of foraminifera, tiny ocean creatures that have floated in the seas for millions of years. When these forams built their shells, they incorporated oxygen from the surrounding seawater. Oxygen comes in two main stable forms, or isotopes, a lighter one and a heavier one called oxygen-18. The key is that when the planet is cold and vast ice sheets lock up the lighter oxygen, the ocean becomes enriched with the heavier oxygen-18. The forams building their shells in this water naturally use more of the heavy isotope. A higher proportion of oxygen-18 in their fossilized shells is a direct chemical signal of an ice age. By analyzing these microscopic fossils from layers of deep-sea mud, we can reconstruct the global temperature with astonishing precision, tracing the rise and fall of ancient climates. This same principle applies on land. The chemistry of ancient soils preserved as rock can trap a record of the atmosphere itself. Certain soils form in a delicate balance with the carbon dioxide in the air, and their chemical composition, particularly the types of clay minerals present, changes with the amount of CO2. By reading this mineralogical code, we can estimate the carbon dioxide levels from a tropical forest 50 million years ago or a barren desert 200 million years ago. These subtle chemical clues, pulled from tiny shells and ancient dirt, allow us to chart the planet's long and volatile climate history. They reveal periods of intense global heat, when palm trees grew near the poles, and epochs of profound cold that gripped the world in ice. This deep time record is our only true context for the rapid changes we see today, proving that our current situation is far outside the natural rhythm of the geological clock. Yet to make sense of this chemical data, we need to know its exact place in the story. How do we arrange all these clues, from fossilized atoms to colossal boulders, into a single, unified timeline? All these clues, from fossilized atoms to colossal boulders, demand a grand filing system. That system is the geologic time scale, the official calendar for our planet's 4.5 billion year history. It is not a simple timeline of years, but a layered narrative built from the ground up, its chapters defined by the most dramatic turning points in the rock and fossil record. The scale is organized into a hierarchy of time, from the largest divisions like eons, which span billions of years, down to the smallest, like epochs, which can cover mere millions. Each of these divisions is marked by a golden spike, a boundary in the rock layers that signifies a fundamental global change. The boundary between the Cretaceous and Paleogene periods, for instance, is literally defined by that thin, iridium-rich layer we find worldwide, the very day the dinosaurs died. This entire calendar is a collaborative masterpiece, painstakingly assembled over centuries by geologists who matched rock sequences from every continent. It gives us a universal language for speaking about deep time, transforming a chaotic jumble of stone into a structured story of planetary evolution. This framework allows us to pick up any fossil, any stone, and place it in its proper chapter within Earth's epic biography. To see this entire timeline laid bare in a single, breathtaking sequence, there is one place on Earth that stands above all others. The Grand Canyon is perhaps the world's most spectacular open geology book, its immense walls exposing nearly 2 billion years of Earth's history. This is not a landscape you simply look at, it is a timeline you physically walk through. As you begin your descent from the rim, you start in a relatively young chapter of the story. The pale Kaibab limestone that forms the canyon's edge was once the bed of a warm, shallow sea, teeming with shellfish and other marine life. With every step downward, you journey further back in time. You pass through layers of sandstone that whisper of ancient deserts, their sweeping dunes frozen in stone. You traverse bands of shale that speak of muddy river deltas and quiet ocean floors. This vertical journey is a direct traversal of the principle of superposition, with the youngest rocks above and the oldest ones waiting far below. After miles of this downward trek through the ages, you finally reach the inner gorge, the very bottom of the canyon. Here, the world changes. The colorful sedimentary layers give way to a dark, twisted, and formidable rock called the Vishnu schist. This is the basement, the true foundation of the continent. This schist was not laid down as sediment, but forged under immense heat and pressure deep within the earth, a testament to a time of monumental mountain building over 1.7 billion years ago. And then you see it, the most profound silence in the entire geological record. Resting directly on top of this ancient, contorted schist is a layer of smooth, rounded river gravel known as the Taypat sandstone. There is no gradual transition, no orderly stack of layers in between. This contact line is called the Great Unconformity, and it represents a chasm in time wider than human comprehension. Over 1 billion years of history are simply missing here, erased by the patient, relentless work of erosion. An entire mountain range was raised and then completely worn down to a flat plain, leaving no trace of its existence in the rock layers. It is a stark reminder that the geological clock does not only record time, it also devours it. For every grand narrative preserved in stone like the Grand Canyon, countless other stories have been lost forever, their pages torn out by the very forces that write them. This beautiful marble statue holds a secret. Its surface is smooth and pure, but the rock it was carved from began as a limestone, a rock that should be packed with the fossilized shells of ancient sea creatures. Those fossils are gone, erased by the immense heat and pressure of metamorphism, which transformed the stone and wiped its biological memory clean. This is the great challenge of reading the geological clock. Its pages are not only missing, they are often rewritten. The most dramatic gaps are called unconformities, and they are the blank chapters in Earth's diary. We already saw the profound silence of the Great Unconformity in the Grand Canyon, where over 1 billion years simply vanished. But unconformities are everywhere. Sometimes an ancient landscape was simply never buried, exposed to wind and rain for so long that entire epochs were weathered away without leaving a trace. Other times, vast layers of rock were deposited, then lifted up and completely stripped off by erosion, their stories carried grain by grain out to sea. These gaps mean the rock record is not a continuous timeline, but a collection of scattered fragments. And then there is the problem of metamorphism. When rocks are buried deep within the Earth's crust or caught in the colossal crunch of colliding continents, they are cooked and squeezed. The minerals within them recrystallize, forming new rocks like slate, schist, and that beautiful marble. In the process, the original textures are often destroyed. A fossil shell is obliterated. The delicate layering of a riverbed is blurred into a shimmering foliation, and the atomic clocks within the minerals can be completely reset. So how can we possibly hope to assemble a coherent history from an archive that is so full of holes and altered pages? Geologists must become master detectives, piecing together clues from the evidence that remains, no matter how fragmentary. Planet holds a secret diary written not in ink but in magnetism. Deep within volcanic rocks, tiny grains of magnetic minerals act like microscopic compass needles. When lava erupts and then cools past a certain temperature, these minerals freeze in place, permanently aligning themselves with the Earth's magnetic field at that exact moment. This locked-in signal is called paleomagnetism, a fossilized echo of our planet's invisible shield. The most astonishing discovery came not from continents, but from the deep ocean floor. As scientists towed magnetometers behind ships, they mapped the magnetic signature of the seafloor basalt. They expected a random pattern, but what they found was a stunningly precise barcode. On either side of the immense underwater mountain ranges known as mid-ocean ridges, the ocean floor was striped with parallel bands of rock. One band would have a magnetic orientation pointing to the north, just like today's field. The very next band would be reversed, pointing south. This symmetrical pattern was the ultimate proof of seafloor spreading. It showed that new ocean crust was constantly being forged at the ridges, and as it cooled, it recorded the current magnetic field. Then, as more magma erupted, this new crust was pushed outward, making room for the next stripe to form. Since we can date the magnetic reversals from lava flows on land, the seafloor stripes become a tape measure for time. The stripes closest to the ridge are the youngest, while those farther away are the oldest, revealing that none of the ocean floor is older than about 200 million years. This magnetic tape recorder allows us to rewind the tape to animate the ancient globe. By reading the paleomagnetic direction in a 300-million-year-old rock from Europe, we can calculate its latitude, placing it near the equator. The same reading from a rock in North America shows it was also near the equator, but on the opposite side of the planet. These invisible magnetic fingerprints are the ultimate evidence for continental drift, proving that the world map is just a single frame in a 4-billion-year-long film. Yet as continents shift and oceans open, life itself carves its own indelible signature into the stone. A dinosaur trackway is more than just a footprint in the mud. It is a frozen moment of behavior, a snapshot of a life in motion. These are trace fossils, the subtle imprints of ancient activity preserved in stone. While body fossils like bones and shells tell us what an organism was, trace fossils tell us what it was doing. A single, winding burrow reveals where a worm tunneled through the seabed in search of food. A complex pattern of scratches on a rock surface records the precise path of a grazing sea urchin from a time long before the dinosaurs. These ichnofossils add a dynamic, behavioral dimension to the geological record, transforming a static scene into a living, breathing ecosystem. They capture moments of life, not just death. Imagine a single layer of rock, an ancient mudflat that hardened into stone. Preserved on its surface are not skeletons, but thousands of crisscrossing tracks. Some are the heavy, three-toed impressions of a large predator, its stride long and purposeful. Interwoven among them are the smaller, more frantic prints of its potential prey. This chaotic tapestry tells a story of a bustling, interactive world that a collection of bones alone could never convey. It reveals population density, movement patterns, and predator-prey interactions, all from the ghostly echoes of footsteps. Yet for all their vivid detail, these ancient traces are still locked within the deep time pages of the rock record. They speak of epochs millions of years in the past. But what about the more recent chapters of Earth's story, events that unfolded just thousands of years ago, far too quickly to be preserved in the slow formation of stone? For these, we must look to a different kind of geological diary, one written not in solid rock, but in the soft, layered pages of ice. A single tree stump can contain a diary of 1,000 years, its rings marking each season of growth with perfect, concentric clarity. This is the heartbeat of the recent past, a pulse we can count year by year. The same principle applies at the bottom of ancient glacial lakes, where nature has been keeping an even more meticulous calendar. These are varves, the thinnest pages in the geological library. Each varve is a pair of layers, a single year's deposit. During the warm summer, meltwater from retreating glaciers would carry coarse, light-colored silt into the lake where it settled quickly. But when winter locked the world in ice, the water grew still. Only the finest, darkest clay particles could drift down through the frozen silence, forming a delicate, dark layer on top of the summer's silt. One light and one dark band equals 1 year. By counting these pairs, scientists can build a timeline back through the last 10 to 15,000 years with the precision of a ledger. This is not a relative sequence, but an absolute count, a year-by-year chronicle of the Holocene epoch. The thickness of each pair tells its own story. A thick, coarse summer layer signals a year of intense melting and warm temperatures. A series of unusually thin, fine varves might point to a prolonged cold snap or a massive volcanic eruption that dimmed the sun and stunted the meltwater flow. These natural archives are so detailed they can even record the dawn of human agriculture, as increased soil erosion from early farming practices washed into the lakes, leaving a distinct signature in the varves. They provide a high-resolution close-up, a frame-by-frame replay of our planet, its most recent major climate shift as the last ice age relinquished its grip. This fine-scale record stands in stunning contrast to the billion-year gaps of the Great Unconformity, proving that the geological clock can tick in both eons and individual seasons. Our own time is now being etched into the planet's permanent record. Geologists are actively debating whether to formally define a new geological epoch, the Anthropocene, an age defined by humanity's profound and global impact. The evidence for this new chapter is already being laid down, a signal so sharp and sudden it will be unmistakable to any future scientist reading the rocks. The mid-20th century will appear as a stark line, marked by the unmistakable signature of radioactive isotopes from nuclear bomb tests. These artificial elements settled across the entire globe, creating a perfect, worldwide timestamp that future geologists will use to pinpoint the base of this proposed new epoch. Alongside this radioactive pulse, they will find a strange, new mineral that never existed before our time: plastic. Microscopic plastic particles are now being woven into marine sediments and lake beds across the planet, forming a permanent, synthetic layer in the mud. The fossil record will tell its own brutal story, showing a sudden spike in extinction rates, a modern mass die-off comparable to the great extinctions of the deep past. And scattered amidst the bones of vanished species will be new, unnatural fossils, the corroded rebar of concrete structures, and the oxidized dust of aluminum alloys. These are the artifacts of our civilization, destined to become the strange curiosities of some distant future. Perhaps the most profound chemical change will be the enormous spike in atmospheric carbon dioxide, a shift so rapid it is literally off the charts of Earth's natural climate rhythm. This spike is being permanently recorded in the ice cores of Greenland and Antarctica, and in the calcium carbonate shells of countless marine creatures, locking our fossil fuel economy into the geological ledger for eons to come. We have become a force of nature, actively writing a new and sobering page in Earth's story. The question is no longer if we are leaving a mark, but what story that mark will ultimately tell. How can we, as individuals, learn to read these signs in the world around us right now? That riverbank or roadside cliff is your own personal portal into deep time. You can stand there today and begin to read the story yourself. Start by looking at the layers. Are they perfectly flat and horizontal like a stack of pancakes? If so, you are likely looking at a period of geological calm, where sediments settled quietly on a stable seafloor or lakebed. But if those layers are dramatically tilted, folded into great arches, or even standing on end, you are witnessing the aftermath of immense force. This is the signature of tectonic collisions, of continents crashing together and crumpling the very crust like a rug. The rock remembers that violence long after the mountains have been worn down. Next, get close and look at the texture. Pick up a piece of rock and really examine its grain. If it's made of large, rounded pebbles cemented together, a rock called conglomerate, you are holding evidence of a powerful ancient river or a turbulent coastline where strong currents rolled and tumbled stones. If the rock feels gritty and looks like compressed sand, you're touching the remnants of a desert dune or a beach. But if it's incredibly fine and smooth, almost like chalk, that's a shale. This delicate rock forms only in the stillest, deepest waters, where the tiniest particles of clay could drift down for centuries in perfect silence. Each texture is a direct clue to a lost world. And then, of course, there are the fossils. You don't need to find a dinosaur skull. A small, spiral shell embedded in the rock, a simple leaf impression, or even a strange, worm-like burrow trace is a monumental discovery. That shell tells you this solid ground was once the bottom of an ocean. That leaf proves a forest once stood where you are standing. These are not just rocks, they are biological telegrams from the past. By training your eye to see these simple things, layering, texture, and fossils, you transform every landscape into a historical document. This is not just an abstract skill, it has profound and urgent applications in our modern world. The same principles that let us read the past are now being used to secure our future. The same principles used to read Earth's ancient story are now guiding our search for the resources that power our modern world. When an oil company drills into the Earth, they are not drilling blindly. They are targeting specific chapters in the planet's history, using stratigraphy to locate the ghostly outlines of ancient environments. They search for porous limestone that was once a coral reef teeming with life, or for a layer of sandstone that formed in the channel of a prehistoric river delta. These are the places where vast quantities of organic matter, the remains of plankton and plants, were buried and cooked over millions of years into the hydrocarbons we call oil and natural gas. The geological clock tells them not just where to look, but when to look, identifying the precise time periods when conditions were perfect for creating and trapping these valuable substances. This same logic unlocks the Earth's mineral wealth. The quest for copper, gold, and rare earth elements is a treasure hunt guided by deep time. These metals do not appear randomly. They are born from specific, violent events in the planetary cycle. Massive copper deposits, for instance, are often found in rocks that formed near ancient volcanic vents on the seafloor, where superheated, mineral-rich water gushed into the ocean. Giant gold deposits are frequently associated with the collisions of continents, events that forced fluids carrying the precious metal up through cracks in the crust, where it solidified into rich veins. By reading the tectonic setting and the absolute age of a rock formation, geologists can pinpoint where these ancient, ore-forming events occurred, turning a mountain range into a geological map for hidden treasure. Perhaps the most urgent application of this knowledge lies in understanding our climate future by reading our climate past. The rocks and ice cores are our only record of how the planet behaves when carbon dioxide levels skyrocket or when global temperatures pivot into an ice age. These are not theoretical models, they are physical data. By studying the geochemical proxies in rocks from a period of intense global warming 55 million years ago, we can see exactly how the oceans acidified, how currents shifted, and how life responded. This deep time context is our calibration tool. It shows us the full range of the Earth's climate system, proving that the speed of the change happening today is unprecedented in the entire geological record. This is not just about curiosity, it is about survival. The story written in stone is one of both cataclysm and profound resilience. Life has endured unimaginable upheavals, but it is the pace of change that determines what survives. We are now writing a new, rapid-fire chapter, and the geological clock is recording every moment. That great dying 252 million years ago is etched into the rock as a silent scream. The End-Permian extinction was the closest life has ever come to being completely erased. The fossil record from this time is a story of collapse told in empty seabeds. In one rock layer, you find a teeming community of ancient sea creatures, a vibrant world of intricate shells and complex marine ecosystems. In the very next layer, there is almost nothing. Just a few hardy, disaster species clinging to existence in a world turned toxic. The cause of this biological annihilation is found not in the sky, but deep within the earth. In what is now Siberia, a colossal volcanic province erupted for nearly 1 million years, flooding the landscape with enough lava to cover the entire planet in 10 feet of basalt. But the lava itself was not the primary killer. It was the gases. These volcanoes belched unimaginable quantities of carbon dioxide and methane, triggering a runaway greenhouse effect that cooked the planet. The oceans warmed, lost their oxygen, and turned lethally acidic, dissolving the shells of any creatures that managed to survive the heat. This was a planet-wide systems failure, a geological crime scene where the rock itself is the witness. These mass extinctions are the great resets of the biological clock. They are not mere setbacks, they are profound evolutionary filters. The KPG asteroid cleared the world of the giant dinosaurs, creating an opening for small, scurrying mammals to step into the sunlight and eventually diversify into everything from bats to whales to us. The Great Dying did the same, wiping the slate so clean that it allowed for the rise of entirely new forms, including the first ancestors of the dinosaurs. Each catastrophe, no matter how devastating, ultimately forged a new and different world. This cycle of destruction and rebirth is a fundamental rhythm of the geological clock, a pulse that reminds us that life is both incredibly fragile and astonishingly resilient. To understand the very first tick of this clock, we must journey back to the beginning of everything, to the formation of the planet itself. The Hadean Eon is the ghost chapter in Earth's biography, a 500 million year period where the rock record almost completely vanishes. This was our planet's violent infancy, a world of global magma oceans under constant assault from the debris of the young solar system. The most dramatic of these collisions involved a Mars-sized body named Theia, whose impact with the young Earth blasted enough material into orbit to coalesce into our moon. The energy from that single event was enough to remelt the entire planet, effectively erasing its earliest surface. So how can we possibly write a history for a time when the very rocks were being destroyed as fast as they formed? We must turn to the only witnesses tough enough to have survived. The microscopic zircon crystals we find embedded in much younger rocks are time travelers from this hellish age. Their incredible durability allowed them to form in that primordial magma and then endure eons of recycling, preserving their original atomic clocks. By analyzing the elements trapped inside these ancient zircons, we find a startling clue. The specific ratio of oxygen isotopes points to a history of interaction with liquid water. This implies that despite the hellish reputation of the Hadean, Earth's surface cooled rapidly enough for water to condense and for solid patches of crust to form, creating the very first landmasses and perhaps even the first oceans. This pushes back the timeline for a habitable world by hundreds of millions of years. We fill in other gaps in this lost chapter by looking to the skies. Meteorites, the leftover building blocks of planet formation, provide a chemical baseline for the early Earth. Their composition tells us what raw materials were available when our world was assembled. The absence of a rock record from the Hadean is, in itself, a form of data. It tells a story of a planet so geologically hyperactive, with such intense heat and bombardment, that preserving a stable surface was nearly impossible. This celestial chaos imprinted a fundamental rhythm on the young planet, a pulse dictated by the mechanics of the solar system that would govern its climate for billions of years to come. The slow, rhythmic pulse of Earth's ice ages is not a random beat, but a melody composed by the planet's dance through space. These vast climatic shifts are orchestrated by predictable changes in Earth's orbit and tilt, patterns known as Milankovitch cycles. Over cycles of 100,000 years, Earth's orbit stretches from a near circle to a slight ellipse, changing our distance from the Sun. Over 41,000 years, the tilt of our planet's axis wobbles, altering the intensity of the seasons. And over 26,000 years, Earth completes a slow wobble on its axis, like a spinning top winding down, changing which hemisphere points toward the Sun at different times of year. These cycles are subtle. They do not change the total amount of energy we receive from the Sun by much, but they dramatically alter its distribution across the globe, tipping the delicate balance between a greenhouse world and an icehouse world. The astonishing part is that these celestial rhythms, written in the mathematics of gravity, are perfectly preserved in mud and stone. In the deep, quiet abysses of the ocean, a continuous snowfall of sediment has been accumulating for millions of years. When scientists pull up long cores of this deep sea mud, they find a climate tape recorder of unparalleled precision. The sediment is not a uniform gray paste, but is composed of beautiful, rhythmic pairs of light and dark layers. The lighter, thicker layers are rich with the fossils of tiny creatures that thrived in warm, interglacial oceans. The darker, thinner layers represent the harsh, barren winters of the ice ages, when global temperatures plummeted and life in the surface waters struggled. By counting these rhythmic pairs, just like counting tree rings or valves, scientists discovered they matched the timing of the Milankovitch cycles perfectly. The 100,000-year cycle of orbital eccentricity is the dominant drummer, setting the pace for the great advances and retreats of the ice sheets. This means the geological clock is not merely a passive recorder of local events. It is synchronized with the grand orbital mechanics of our entire solar system. The very mud at the bottom of the sea holds an echo of our planet's celestial journey. This entire story, from atomic clocks in zircons to orbital rhythms in mud, compels a profound reflection. We are not just living on this planet, we are living within its ongoing, multi-billion-year biography. The ground we walk on is a dynamic archive, and the air we breathe is a chapter in a chemical saga that began with the rusting of the oceans. The geological clock gives us the ultimate context for our own existence, revealing both the incredible resilience of life and the devastating power of rapid change. We have now become a force capable of writing this story ourselves, etching our own chapter into the permanent stone and ice. The clock is ticking, recording every decision, and the next page is ours to write. Human civilization occupies less than a single tick on the great geological clock. Our entire recorded history, from the first cities to the present day, is a whisper in a 4.5 billion-year epoch. This concept of deep time is perhaps the most humbling and transformative idea to emerge from reading the rocks. It shrinks our human dramas and triumphs to an almost invisible scale, yet it simultaneously grants us a unique and awesome responsibility. We are the first species we know of to have unearthed this planetary autobiography and understood its chapters. We can hold a fossil trilobite in our hand and comprehend that it lived in an ocean that vanished hundreds of millions of years before the first dinosaur walked. This knowledge fundamentally shifts our place in the universe. It dismantles the idea that the world was made for us, revealing instead that we are a very recent, albeit remarkably clever, arrival in a story that was already ancient. The rocks teach a powerful lesson in resilience. They show us that life has been nearly wiped out multiple times, only to return in new and unexpected forms. They show us that continents are transient and that even the mightiest mountain ranges are eventually ground to dust. This is not a story of fragility, but one of immense, persistent endurance. Yet the same record also screams a warning about the pace of change. The most devastating extinctions in Earth's history were not the slow, grinding ones, but the sudden, violent shocks that gave life no time to adapt. We now hold the power to create just such a shock. Our actions are scribing a new layer into the planetary archive, a stratum rich in plastic, radioactive isotopes, and a rapidly shifting climate signal. For the first time, a conscious force is directing a major chapter of the geological story. This connects the scientific pursuit of geology to the most profound human questions. Where did we come from? What is our role here? The answers are not written in the stars, but in the stone beneath our feet. They tell us we are part of an intricate, interconnected system that operates on a scale beyond our everyday perception, and that our fleeting moment in the sun comes with a profound duty to protect the ongoing narrative of this living world. The story of the Great Geological Clock is ultimately a testament to human curiosity, a saga pieced together by patient observation and brilliant deduction. It reveals a planet in constant, dynamic flux, where mountains rise and fall to the rhythm of drifting continents, and life itself is shaped by the slow, relentless ticking of deep time. Our journey has taken us from the simple logic of superposition to the atomic precision of Zircon crystals. From the silent scream of mass extinctions to the stark line, we are now drawing with our own hands the proposed Anthropocene. This magnificent record is far more than a history book. It is a vital guidebook for our future. Within its pages are critical lessons on the causes and consequences of climate change, the sustainable management of Earth's finite resources, and the incredible, enduring resilience of life in the face of catastrophe. The next time your eyes trace the layers of a canyon wall or your fingers brush against a simple stone in a stream, remember that you are holding a page from our planet's epic autobiography. It is a story that belongs to all of us. I would love to hear what you think. Have you made any geological discoveries in your own corner of the world? Share your thoughts and findings in the comments below. And if you enjoyed this journey through the deepest chapters of our planet's past, please subscribe for more explorations into the wonders and mysteries of the world we call home.